Pressure and force acting on this drum caused it to collapse. In this unit, we're going to talk about pressure and force in depth, and we'll find out how they're measured and how they apply to plant functions. You must understand what force and pressure are all about and how they relate to plant equipment in order to run your plant safely and efficiently. Well, let's begin by taking a look at force, what it is and how it relates to pressure. Now, when we think of force, we might think of the motion caused by a force, such as the force applied by a forklift to move a container, or the force of steam pushing against the moving blades of a turbine. Now, these examples have to do with how force applied to an object usually causes movement. But movement is not always the result of force being applied to objects. For instance, have you ever tried to open a valve that was stuck? You were applying force, but the valve wouldn't budge. So we can describe force as any influence that is capable of producing movement or a change in motion. What you've seen so far is that force can be exerted by solids. For instance, you might remember the example of a coal car used for transporting coal to a plant. The coal exerted a force on the bottom of the car equal to the weight of the coal. So one way of describing force is the total weight applied to a surface. We can express force in units of pounds. Now, so far we've only been concerned with the force exerted by solids. Fluids also exert force. For instance, you may remember that in the last unit we talked about two containers, one holding a cubic foot of water, the other holding a cubic foot of mercury. We found that the water exerted a force of about 62.4 pounds, and the mercury exerted a force of about 848.6 pounds. But liquids such as water and mercury are only one type of fluid. Another type, gas, also exerts force. A good example is the air surrounding the Earth. It's a sea of fluid exerting force on the Earth's surface. So we can restate our description to say that force is the total weight applied to a surface by a solid, liquid, or gas. We can use this description in turn to help define pressure. Now, pressure is force per unit area. A common unit of pressure is pounds per square inch, which is abbreviated psi. Let's take a look at the containers of water and mercury again so we can see the relationship between force and pressure. The force exerted by the water is about 62.4 pounds, while the pressure is 0.433 psi. The cubic foot of mercury exerts a force of about 848.6 pounds and a pressure of about 5.89 psi. To make the relationship between force and pressure clearer, we'll look at a tank with a water level of 10 feet and a bottom surface area of 50 square feet. The tank contains 3,757 gallons of water. To find the force the water is exerting on the bottom of the tank, we must calculate the total weight of the water pushing down over the entire 50 square feet. We do that by multiplying the number of gallons by the weight of 1 gallon of water. A gallon of water weighs about 8.3 pounds. So 3,757 gallons times 8.3 pounds per gallon results in a weight of about 31,183 pounds. Well, therefore, we have 31,183 pounds of force pushing down on the bottom of the tank. But if we consider the pressure being exerted by the water, we must find the force that is pushing down on each square inch of the bottom of the tank. You may remember that pressure can be found by dividing force by area. So, to find the pressure on the bottom of the tank, we would divide the force, 31,183 pounds, by the area, 50 square feet. To change square feet to square inches, we'll multiply the 50 square feet by 144 for a total of 7,200 square inches. And doing the math results in an answer of about 4.33 psi. The force is 31,183 pounds, and the pressure is 4.33 psi. Now, this example shows that when force is applied over an area, it results in a pressure, because pressure is force per unit area. Well, we've seen what force is, and we've looked at the difference between force and pressure. This is a good time to stop the tape and review that material in your text. If you have any questions, ask your instructor to help you. If the water in a tank is 1 foot deep, we know that the pressure exerted by that water on the bottom of the tank is 0.433 psi. What we now need to consider is that the pressure in a tank can be due to more factors than just the pressure exerted by the liquid in the tank. We'll look at one of those other factors, gas pressure. Now, some common gases used in plant tanks are air, steam, and nitrogen. Let's look at an example where steam affects the pressure in a tank. Now, what we're going to do here is show how this steam contributes to the total pressure exerted on the bottom of a tank. But before we do, let's try to understand why steam would be put into a tank in the first place. For our example, we use a storage tank that could represent any one of the many storage tanks in the plant. Let's say the tank contains water, and we're concerned about corrosion caused by oxygen in the water. Now, since storage tanks are almost never completely filled with water, the empty space at the top will be filled with air. Air contains oxygen, and some of the oxygen will be absorbed by the water. Oxygen in the water causes a problem, namely corrosion. And the greater the oxygen content of the water, the greater the tendency for metal parts to corrode. If the air at the top of the tank is displaced by a blanket of steam, then the amount of oxygen absorbed will be greatly reduced, and corrosion to the tank and to plant systems will be minimized. Typically, a steam blanket will exert 15 to 16 psi on the tank. This means the total pressure in the tank is a result of two factors, the steam blanket and the height of the water. To determine total pressure, we would add the two factors. Let's say the storage tank has 30 feet of water in it. The pressure exerted by the 30 feet is 30 times 0.433, or approximately 13 psi. Let's say the steam blanket exerts 15 psi. So the pressure due to these two factors is 13 plus 15, which equals 28 psi. What's important here is that the pressure on the bottom of the tank is the sum of all the sources of pressure in the tank. Now, one thing is always true of the pressure in a tank. It's exerted in all directions. Now, we can see this if we consider the placement of a suction pipe in a tank. The most common notion would be that the inlet to the suction would have to be placed upward in order to allow pressure to be exerted fully on the suction. But in reality, most suctions are pointed downward. And this is possible because the pressure at the point where the suction is taken is exerted equally in all directions. Now, therefore, the pressure upward at that same point is the same as the pressure downward, and to all sides. The direction the suction inlet faces has no effect on the pressure at the suction. There is another factor to consider when we talk about pressure. Earlier, we said that the air surrounding the Earth is a gas, and like all other gases, it exerts a pressure. And like the steam and water in the storage tank, it also exerts pressure at a given point equally in all directions. At sea level, the average pressure exerted by the atmosphere is 14.7 pounds per square inch. The effect of pressure being exerted equally in all directions can be demonstrated by considering the way atmospheric pressure affects the steel drum that we saw at the beginning of this unit. We're using this drum because we don't want to damage a working tank. Even though the drum is smaller than a large tank, both it and a tank will be affected in the same way by a difference in pressure. If we look at a cutaway view of the drum, we can see that atmospheric pressure is exerted equally both inside and outside the drum, and on the top, bottom, and all of its sides. This is an example of balanced forces, and the result is that the drum doesn't collapse or rupture. But if we seal the opening of the drum and begin drawing fluid out of it, the pressure decreases inside. The greater force of atmospheric pressure on the outside of the drum causes it to collapse. Well, let's return the drum to its normal configuration and consider what would happen if we force air into it. Eventually, the pressure in the drum gets high enough to rupture it. Decreasing or increasing the pressure on the inside of the drum is an example of differential pressure creating an imbalanced force. The pressure acting on the inside of the drum is not the same as the pressure acting on the outside of the drum, and it collapses or ruptures because it's not designed to handle the force produced by the difference in pressure. The force that difference in pressure exerts is determined by the total area the pressure acts on. Even if the pressure difference is very small, if it's over a large area, a great deal of force can be applied. If you've ever looked at the water boxes on a condenser, you may have wondered why they're so heavily constructed. Well, this seems uncalled for when you consider that typically the pressure in the water box is no more than 17.7 psi. Since atmospheric pressure is about 14.7 psi, we can see that by subtracting 14.7 from 17.7, that there is only a 3 psi difference between the pressure inside the water box and the pressure outside the water box. But when you consider the force acting on the water box, the purpose of this heavy construction becomes clear. We can find the force by multiplying pressure difference across the water box by its area. A typical water box might have about 86,400 square inches of surface area. When we multiply this times the 3 psi difference in pressure, we get a total force of about 259,200 pounds acting on the water box. It must be constructed to withstand this great amount of force. Well, let's review what we've covered so far. We found that pressure on the bottom of a tank is the sum of all the sources of pressure in the tank. We discussed the fact that pressure is exerted equally in all directions. And we talked about atmospheric pressure and total force. In our next segment, we'll look at some instruments for monitoring atmospheric pressure. For now, turn off the tape and read your text. If you have any questions, ask your instructor to help you. In the last segment, we talked about pressure exerted by the air, atmospheric pressure. We said that at sea level, atmospheric pressure exerts an average of 14.7 pounds per square inch on the Earth's surface. However, this value for atmospheric pressure can and does vary, depending on weather conditions. These variations affect pressure readings throughout plant systems, making it necessary for you to be able to account for these changes. In this segment, we'll talk about how changes in atmospheric pressure are measured. You've probably heard the weathermen talk about high pressure and low pressure areas, and you might have wondered how weather conditions affect air pressure. Well, there are many factors that can cause increases and decreases in atmospheric pressure, so many that we can't go into all of them here. But in general, these changes are caused by large-scale movements of the atmosphere around the Earth. Air warms near the equator and cools near the North and South poles. The rate of cooling, heating, and movement of the air, coupled with the Earth's rotation, are largely responsible for the atmospheric pressure variations. Now, these varying weather conditions affect atmospheric pressure over large areas of the Earth, sometimes hundreds of miles. If a low air pressure front moves into an area where your plant is located, the atmospheric pressure in the plant will change, causing some pressure readings to change also. The atmospheric pressure in the plant is usually measured and displayed by a device called a barometer. The reading from the barometer may be used to adjust other pressure readings if necessary. Now, about 300 years ago, a scientist named Torricelli invented the barometer while trying to prove the existence of atmospheric pressure. Torricelli set up a demonstration using mercury, a glass tube, and a bowl. Now, these materials are very similar to those presently in use, but today we wouldn't handle mercury with our hands because we know it's poisonous. Now, first, he poured some mercury into the bowl. Next, he filled the tube completely with mercury. Then he sealed the open end to prevent any air from entering the tube. He placed the sealed end of the tube in the bowl of mercury, and then he unsealed it. At first, the mercury began to flow out of the tube, dropping the level of mercury. And then the flow of mercury out of the tube stopped. Atmospheric pressure caused the mercury level in the tube to hold steady. Air pressure pushed down on the mercury in the bowl, preventing all the mercury from flowing out of the tube. The flow of mercury into the bowl stopped when the column of mercury in the tube was exerting the same amount of pressure as the atmosphere. In other words, the pressures from the mercury and the air were balanced. Now, today, barometers are constructed in much the same way. A tube is filled with mercury and placed in a container of mercury. The height of the mercury column reflects the atmospheric pressure. A scale alongside the mercury column allows the mercury column to be read in inches of mercury. As atmospheric pressure changes, so does the height of the mercury in the tube. If atmospheric pressure increases, the height of mercury increases. And if atmospheric pressure decreases, the height of the mercury decreases. At a typical 14.7 psi atmospheric pressure, the barometer will read 30 inches of mercury. We can show this mathematically. Remember that the pressure of fluid in a column can be found by multiplying density times height. To find the density of mercury, we can start by looking up its specific gravity. Now, looking at this table, we find that mercury has a specific gravity of 13.6, which means that mercury is 13.6 times as dense as water. To find the density of mercury, we multiply its specific gravity times the density of water. The density of water is 62.4 pounds per cubic foot. Multiplying the specific gravity of mercury, 13.6, times the density of water, 62.4 pounds per cubic foot, we find the density of mercury to be 848.6 pounds per cubic foot. For the purposes of this discussion, we'll need to know the density per cubic inch. So we'll divide 848.6 pounds per cubic foot by 1,728 cubic inches per cubic foot. And we get a density of mercury of 0.49 pounds per cubic inch. Well, now that we know the density and the height of the mercury in the column, we can use the equation density, rho, times height, h, to find the pressure, P. The density, 0.49 pounds per cubic inch, times height, 30 inches, equals a pressure of 14.7 pounds per square inch. Okay, we said that the flow of mercury out of the tube stops when the atmospheric pressure and the pressure exerted by the mercury in the tube are the same. In our example, both pressures were 14.7 psi. This is another example of balanced forces. Now, if the mercury level in the barometer holds steady at 30 inches, we can conclude that atmospheric pressure must be 14.7 psi. We say that barometers are used to measure the atmospheric pressure, but a barometer actually reads inches of mercury, not pounds per square inch, which is how we usually express pressure. If you need to use a barometer reading to compensate other pressure readings for changes in atmospheric pressure, you'll need to be able to convert from inches of mercury to psi. For example, if there is low pressure, the barometer may drop and read 29 inches of mercury. We need to convert this reading of inches of mercury to pounds per square inch in order to find the pressure exerted by the mercury. We can do this the same way that we found the amount of pressure exerted by 30 inches of mercury, by multiplying the height of the mercury, 29 inches, times 0.49 pounds per cubic inch. But an easier way to find the pressure is to remember that each inch of mercury is equal to a pressure of about 1/2 a pound per square inch. So 29 inches of mercury is roughly equivalent to an atmospheric pressure of 14.5 psi. You might want to remember that 1 inch of mercury equals about 1/2 a psi, and 2 inches equals about 1 psi. Now this will help you to make a rough conversion from inches of mercury to pounds per square inch. Well, now that we've seen how a barometer measures atmospheric pressure, let's look at how to read other types of pressure measuring devices, such as gauges. In order for you to read these devices correctly, you'll need to know the difference between the designations psia and psig, which are marked on a gauge face. Psia stands for pounds per square inch absolute, and psig stands for pounds per square inch gauge. A gauge that reads psia includes atmospheric pressure in its reading. For example, if we were reading pressure at the bottom of a tank filled with 10 feet of water, we know that the pressure due to the water is 10 times 0.433. This is approximately 4.3 pounds per square inch. But there is also additional pressure exerted as a result of atmospheric pressure, about 14.7 pounds per square inch. So a gauge that reads pounds per square inch absolute will show the 4.3 pounds per square inch exerted by the water plus the 14.7 pounds per square inch exerted by the air. This gives us a total pressure reading of 19 psia. Now, a gauge that measures psig would read only 4.3 psig. That's because atmospheric pressure is not included in the reading. And the difference between psia and psig is the amount of pressure exerted by air. This equation will help you to remember the difference. Psia equals psig plus atmospheric pressure. Okay, in this segment, we've seen how a barometer is constructed, how to read it, and how to find the atmospheric pressure in inches of mercury. We've also talked about the difference in gauges measuring pressure in terms of psia and psig. For now, stop the tape, read your text, and ask your instructor any questions you have. Next, we'll talk about what happens when pressure drops below 14.7 psia. This is the barometer we saw in the last segment. Did you wonder what was in the space at the top of the barometer? There's no mercury and there's no air. This space is a vacuum, an area where there is virtually zero pressure. In this segment, we'll talk about vacuum and how it is measured. Now, we said earlier that atmospheric pressure varies according to weather conditions. However, for our discussion in this segment, we'll choose one value, 14.7 psia, for atmospheric pressure, and we'll assume that it doesn't change. Vacuum is pressure less than atmospheric, that is, less than 14.7 psia. We can talk about vacuum in two ways, total vacuum and partial vacuum. A total vacuum is 0 psia. A total vacuum is basically a theoretical idea that's virtually impossible to achieve in real life. Take a condenser, for example. For there to be a total vacuum in a condenser, every molecule of air would have to be removed. As you can imagine, that's an impossible task. In most cases, when we speak of a vacuum, we're talking about a partial vacuum. A partial vacuum is a pressure between 14.7 psia and 0 psia. Now we can also use psig to describe a vacuum. Since 14.7 psia is the same as 0 psig, then a vacuum is anything less than 0 psig. A total vacuum would be negative 14.7 psig. This chart shows the relationship between psia, psig, and vacuum. We've already established atmospheric pressure at 14.7 psia, or 0 psig. If pressure drops below 14.7 psia, or 0 psig, a partial vacuum exists, and pressure in psig becomes negative, ranging from 0 to negative 14.7. In places in the plant, such as the main condenser, vacuum may be measured in inches of mercury. Inches of mercury can be expressed in two ways: inches of mercury absolute and inches of mercury vacuum. Now this can be shown more clearly if we look at the devices used to measure vacuum. Usually they're labeled vacuum. The devices are called manometers. A vacuum manometer is similar in construction to a barometer. Whether a manometer reads inches of mercury absolute or inches of mercury vacuum depends on how it's connected. First, we'll look at a manometer that measures inches of mercury absolute. Now, here's the condenser, and here is the manometer. And notice that the manometer looks a lot like a barometer, except the bottom is sealed and connected to the condenser. In this way, the pressure in the condenser pushes against the mercury in the container. Now, when the condenser is shut down and vented to atmosphere, there's 14.7 psia pressure in the condenser. Now, this 14.7 psia pushes down on the mercury and pushes it up the tube to a height of 30 inches. When a unit is started up, a vacuum is drawn in the condenser. One way of doing this is with vacuum pumps that are connected to the condenser. When the vacuum pumps are started and air is drawn from the condenser, the column of mercury begins to drop. When the pressure in the condenser reaches 10 psia, the column of mercury is at a height of about 20 inches. If a total vacuum could be reached in the condenser, there would be 0 psia, and the column of mercury would be 0 inches. When we measure vacuum this way, the scale is known as inches of mercury absolute. Another way of writing inches of mercury absolute is inches Hg absolute, since the chemical symbol for mercury is Hg. Inches of mercury absolute is also known as back pressure. If the back pressure in the condenser reads 2 inches of mercury absolute, then the pressure in the condenser is about 1 psia. You may recall that 1 inch of mercury equals about half a pound of pressure. Well, you can use this fact to quickly estimate a manometer reading in psia by dividing the height of the mercury in inches by 1/2. Now, this will give you a rough estimate of the pressure in the condenser in psia. Okay, now let's look at the way we measure inches of mercury vacuum. Here's the condenser, and here's the manometer. This manometer looks quite different from the one we just looked at. It's made up of a tube in which the top end is connected to the condenser, and the other end is inserted into a container of mercury. Atmospheric pressure pushes down on the mercury in the container, trying to force it up into the tube. The condenser vacuum pushes at the other end of the tube, trying to push the mercury out of the tube. When the condenser is shut down and at atmospheric pressure, the pressure on both ends of the tube is the same. Since the pressure is balanced, no mercury is pushed into the tube, and the mercury level is 0. Now, as the vacuum pumps are started and pressure in the condenser decreases, the mercury begins to rise up the tube. In other words, the mercury begins to flow from the higher pressure in the atmosphere toward the lower pressure in the condenser. At a pressure in the condenser of 10 psia and an atmospheric pressure of 14.7 psia, the mercury column would be about 10 inches high. And if it were possible to reach 0 psia, the column would rise to 30 inches. You may have noticed that a scale measuring inches of mercury vacuum works in the opposite direction as a scale that measures inches of mercury absolute. It's worthwhile to remember that 30 inches of mercury vacuum is equal to 0 inches of mercury absolute. And this is a relationship you must know in order to convert between vacuum and absolute scales. Now, keep in mind that vacuum, measured in inches mercury vacuum, is really a comparison between the pressure in the condenser and the atmospheric pressure. Therefore, if atmospheric pressure changes, so will the reading in inches of mercury vacuum. Now, in order to find the actual pressure in the condenser, or the back pressure, it's necessary to make corrections for variations in atmospheric pressure. To make these corrections, we use a manometer and a barometer, which you'll find in most control rooms. First, we take two readings, one from the manometer, measuring the inches mercury vacuum in the condenser, and one from the barometer, measuring atmospheric pressure. Then, to get the back pressure, subtract the inches mercury vacuum reading from the barometer reading. For example, if the barometer reads 28 inches and the mercury vacuum reading is 26 inches, the back pressure is 28 inches minus 26 inches. This results in a back pressure of 2 inches mercury absolute. Okay, now we've seen how vacuum works, and we've looked at the two ways vacuum is measured. And this chart will help us review the relationship between inches mercury absolute, psia, and inches mercury vacuum. Again, we'll assume atmospheric pressure is 14.7 psia. At atmospheric pressure, vacuum is 30 inches mercury absolute and 0 inches mercury vacuum. At 10 psia, vacuum's about 20 inches mercury absolute and 10 inches mercury vacuum. And finally, at 0 psia, there are 0 inches mercury absolute and 30 inches mercury vacuum. Well, we've looked at quite a bit of material in this segment, and we'll stop here and let you review what we've covered. Read the text and answer the questions. If you have a problem with the material, ask your instructor to give you a hand.
Discharge pressure on the mills, make sure you don't load up any mills and trip them out.
I heard you guys had a problem with number 2 fuel oil tank.
Yeah, we were going to pump the oil out of it, and the vent valve was automatic vent valve was corroding shut. So it didn't open up, and we pulled a vacuum on the tank, collapsed the sides in on it. Quite a bit of repair work there to do.
Did somebody take out that pump?
Well, I don't know. It should be in the logbook. Let's see here. Yeah, Mary tagged it out.
The problem these operators are talking about was caused by pressure, force, and the compression and expansion of gases. That's what we'll be talking about in this unit. We'll see how these principles work and how they're used in plant operation. Now, first of all, we must understand that all matter is composed of very small particles called molecules, which are in constant motion. The molecules are so small that it's impossible to see them, or the space between them with the naked eye. The form that matter takes is related to the amount of this space between the molecules. For instance, in matter that takes the form of a solid, the molecules are much closer to each other than they are in matter that takes the form of a gas. Well, this is evident when we try to compress matter, actually pushing the molecules closer to each other. The compression of a solid object is almost imperceptible, while gases can be very noticeably compressed. Now, in the case of a gas, there is a relationship between the pressure applied to a gas and the amount of compression that takes place. As the pressure of a confined gas increases, the volume decreases proportionately, as long as the temperature is held constant. If we place some gas in a cylinder and apply force with a piston, the gas will be compressed. If the force applied to the gas is doubled, the volume decreases by half. Now, this is expressed mathematically by the equation P1 V1 equals P2 V2. P1 stands for initial pressure, and V1 stands for the initial volume. P2 stands for the pressure of the gas after compression or expansion. V2 stands for the volume after compression or expansion. Now, this relationship is called Boyle's law, in honor of the physicist who discovered it. The pressure used for P1 and P2 must be in psia. If psig is used, then the answer will be wrong. Remember, to convert psig to psia, add atmospheric pressure to the psig reading. In your plant, Boyle's law applies to many areas of operation. We'll look at how Boyle's law functions in two of these situations: air compressors and storage tanks. But first, let's look at a theoretical example of how Boyle's law actually works. The idea of gas compression is shown by this tank with a piston attached. The tank is filled with air, which is pressurized by the weight of the piston pushing down on it. We'll start with a pressure of 25 psia and a volume of 200 cubic inches. If we add enough weight to double the force on the gas, the pressure on the tank doubles to 50 psia, and the volume is reduced to 100 cubic inches. Notice that the pressure of the gas doubles and the volume reduces by 1/2. Now we can show that the equation for Boyle's law predicts this by putting the figures in our example into the equation. We started with 25 psia for P1 and 200 cubic inches for V1. Now, we only need one final condition to calculate the other. For example, we can calculate the final pressure if the final volume is 100 cubic inches. To solve the equation, we'll divide both sides by 100 cubic inches. 100 cubic inches cancel on the right side, leaving only P2. When we do the math, we find P2 equals 50 psia. The answer agrees with what we discussed earlier. This equation can be used with any starting conditions, as long as pressure is expressed in psia. Changes in gas volume are not only related to pressure changes, but they're also related to temperature changes. If a gas is cooled steadily while maintaining a constant pressure, the gas volume steadily decreases. If the gas is heated and pressure is held constant, its volume increases. Now, this can be illustrated with a graph. The vertical line is volume, and the horizontal line is temperature. Volume of a gas is less at 32 degrees Fahrenheit than it is at 212 degrees Fahrenheit. If we continue to lower temperature until it reaches minus 460 degrees Fahrenheit, volume appears to go to zero. In reality, this wouldn't happen because the gas would liquefy before that point. Nevertheless, minus 460 degrees Fahrenheit does have a special significance. Earlier, we said that molecules are constantly in motion. But if temperature gets cold enough, all movement of molecules stops. This happens at minus 460 degrees Fahrenheit, and it's called absolute zero, which is the beginning point for an absolute temperature measurement called the Rankine scale. 0 degrees Rankine is absolute zero. 492 degrees Rankine is the freezing point of water, and 672 degrees Rankine is the boiling point of water. Now, this is important because if we add temperature to Boyle's law, the temperature must be expressed in the absolute temperature scale. The equation for considering temperature is P1 times V1 over T1 equals P2 times V2 over T2. This is Boyle's law with temperature added. T1 is the initial temperature and T2 is the final temperature. Now, the catch with this equation is that the temperature must be expressed in absolute temperature. Otherwise, the calculation will come out incorrect. We'll find that in most situations where a gas is compressed, all three factors, pressure, volume, and temperature, must be accounted for. We'll take a look at some practical applications of Boyle's law in the next segment. For now, review the material on expansion and compression of gases and work the problems in the textbook. We now know that pressure, volume, and temperature of a gas can be calculated by the equation P1 times V1 over T1 equals P2 times V2 over T2. Well, let's take a look at an in-plant application where this equation and the principles behind it are evident. Air compressors. Air compressors purposely apply the fact that the pressure of a gas increases proportionately as its volume decreases. Let's look at how a typical reciprocating air compressor works. The parts of an air compressor are a cylinder, a piston, an inlet valve, and a discharge valve. The piston is moved back and forth in the cylinder by a motor. When the piston moves back, air at atmospheric pressure is drawn into the cylinder. As the piston continues through its cycle, additional air is drawn into the cylinder. Then, on the in-stroke, the air is compressed, causing its pressure to increase. At the end of the stroke, the discharge valve opens and the pressurized air is released. Then the cycle repeats itself. If you've ever been around air compressors, you know that they get hot when they're operating. This is typical of compressed gases. In most cases, when gases are compressed, they increase in temperature. Or if gases are expanded, they decrease in temperature. These changes must be accounted for. So we'll use the equation that includes temperature. But keep in mind that the temperature must be expressed in absolute temperature. We'll use the Rankine scale. We'll start with an initial pressure of 14.7 psia, and we'll determine the final pressure when we compress the initial volume of 1 cubic foot of air to 1/10 of its original volume. We'll consider the starting temperature of the air as 70 degrees Fahrenheit, or 530 degrees Rankine, and the final temperature of the air as 180 degrees Fahrenheit, or 640 degrees Rankine. Now, we'll take the equation P1 times V1 over T1 equals P2 times V2 over T2, and solve for P2. To do this, we multiply both sides of the equation by T2 over V2. On the right side of the equation, T2 times V2 cancel, and we're left with T2 times P1 times V1 over V2 times T1 equals P2. T2 is 640 degrees Rankine. P1 is 14.7 pounds per square inch. V1 is 1 cubic foot. V2 equals 0.1 cubic foot. Now remember, we're decreasing the volume to 1/10 its original size. And T1 is 530 degrees Rankine. When we multiply this out, we get about 122 pounds per square inch for P2. So, by reducing the volume by 1/10 and allowing the temperature to increase from 530 degrees Rankine, or 70 degrees Fahrenheit, to 640 degrees Rankine, or 180 degrees Fahrenheit, we increase the pressure from 14.7 psia to 122 psia. Well, now let's look at another application of Boyle's law that you'll find in your plant. We'll see the importance of venting an enclosed tank that's being filled. Let's consider an oil tank with an air volume of 4 times 10 to the 6 cubic inches. The air pressure in the tank is initially 14.7 psia. Now, we want to calculate what happens to the air pressure in the tank as we begin to fill it. We'll find the pressure after we've reduced the air volume in the tank to 4 times 10 to the 5th cubic inches. Because the tank is so large and it takes a long time to fill it, the temperature change is negligible, and we can use the equation P1 times V1 equals P2 times V2. P1, the initial pressure in the tank, is 14.7 pounds per square inch absolute, and V1 the initial gas volume in the tank, is 4 times 10 to the 6 cubic inches. P2 is the unknown, the final pressure we're going to calculate. And V2, the final gas volume, is 4 times 10 to the 5th cubic inches. We can now put these figures into the equation. P1 times V1 equals P2 times V2. 14.7 psia times 4 times 10 to the 6th cubic inches equals P2 times 4 times 10 to the 5th cubic inches. Next, we divide both sides of the equation by 4 times 10 to the 5th cubic inches. We get 14.7 psia times 4 times 10 to the 6th cubic inches divided by 4 times 10 to the 5th cubic inches equals P2. And doing the math, we find P2 equals 147 psia. The pressure inside the tank is 147 psia, and the pressure outside the tank is 14.7 psia. Now, as we said before, the difference in pressure between the inside and the outside of a tank can result in a great deal of force being applied to the tank walls. In this case, the tank would rupture if it's not designed to handle the differential pressure that occurs when the oil fills the tank and the air is compressed. We find the differential pressure by subtracting the lower pressure outside the tank from the higher pressure inside the tank. 147 psia inside minus 14.7 psia outside equals 132.3 psi difference in pressure. If the tank is enclosed, the differential pressure would cause it to rupture. For this reason, enclosed tanks are equipped with a vent valve. You should make sure that a tank's vent is open before you begin filling it. Remember, we said that fluids flow from high pressure to low pressure areas. With the vent valve open, the air inside the tank at a higher pressure will flow through it toward the lower pressure outside the tank, and the difference in pressure between the inside and outside of the tank will equalize. Boyle's law also applies when draining a tank with the vent valve closed. We'll use this 55-gallon steel drum we saw at the beginning of this unit. The drum is filled with water and is attached to a receiver, which in turn is connected to a vacuum source. When we open the drain valve and remove the water, a vacuum is drawn, and the pressure inside the drum decreases. As the pressure decreases, the higher atmospheric pressure outside the drum pushes on it, causing it to collapse. Even though the drum construction is quite sturdy, you can see the great amount of force applied as a result of the differential pressure between the lower pressure inside and the higher pressure outside the drum. It's a good idea to always make sure vent valves are open when you drain or fill tanks. In this segment, we've talked about the conditions resulting from the compression and expansion of gases, and we've seen how Boyle's law relates to plant operation. Throughout this unit, we've talked about pressure and how it relates to liquids and gases. We've seen how to measure atmospheric pressure and vacuum in the plant. And we've showed you some of the ways these things relate to your job as an operator. We'll now take some time to review the material in your text. And if you have any questions, ask your instructor to help.